everyone, my name is Melissa Boudreau and I will be doing my third presentation over numerical analysis. In this presentation, I will just be covering just a couple different questions that cover different areas of this subject, so let's get started. So for this question, I had pulled it from the first exam that we took, question 5, and it's asking us to find the Lagrange, some people pronounce it Lagrange, interpolation polynomial for the following points, and we're given three distinct points, -2 and 3, 0 and 1, 1 and -1. So to solve this, we need to use Lagrange interpolation. It's a method and it's used to interpolate between any given points by fitting a curve between them. And the complexity of the curve depends on its order, which also determines which points it passes through. So there are different orders when it comes to polynomials, and the first order we would just call this linear, which is just basically a line that passes through 2 points. We have second order, which passes through 3 points. We will call this quadratic. And we have third order, which passes through 4 points, and we would just continue with this. So this image, I had actually pulled it from the book that was used in this course last semester, and it's a little difficult to understand firsthand, but it's basically the summation of the Lagrange terms multiplied by the function terms. And so all of this is just a brief intro to Lagrange interpolation, and we'll be applying this concept to the problem. So since we are given 3 data points, we're going to end up with 3 terms. And we're first going to assign each x and y to its correct term. So we're going to take the first point, -2 and 3, and assign -2 to be our x1 and assign 3 to be our y1. And we will continue this with all of our given points. So for the second point, 0 and 1, 0 will be our x2 and 1 will be our y2. And for the third and last point, 1 and -1, 1 will be our x3 and -1 will be our y3. And I included a table off to the side just to help get a better visual of what we're doing. So according to Lagrange interpolation, remember that we are looking for the interpolation polynomial, which is the product of the summation of the Lagrange terms and the function terms that I had stated in the previous slide. So for the first equation, this is just a general expression that I've written, and we're going to walk through this. So we're going to start off with y1 multiplied by a fraction. And the numerator of the fraction is going to be the product of the differences between x and all of our given x's that are not x1. So one thing I want to make clear here is that x is a variable, so just be sure not to confuse this x with our x1, x2, and x3. So back to the numerator, since we are only given 3 points, we're going to have x minus x2 multiplied by x minus x3. And as for the denominator, it's going to be the product of differences between x1 and all of the x's that are not x1. So in this case, we will have x1 minus x2 multiplied by x1 minus x3. So this first part here is going to be our first term of the Lagrange polynomial, and we will continue to do this. So for the next one, we will have y2 multiplied by another fraction. This fraction is going to be the product of each variable subtracted from all of our given x's that are not x2. So then we will have x minus x1 multiplied by x minus x3. Then for the denominator, we get to use our x2 and subtract from each of our given x's that are not x2. So we have x2 minus x1 multiplied by x2 minus x3. This is our second term for the Lagrange polynomial. And we will continue once again and have our y3 multiplied by the same type of fraction, where the numerator is the product of each variable x subtracted from all of our given x's that are not x3. and this ends up being x minus x1 multiplied by x minus x2. The denominator is the same idea as I stated before, where in this case we use our x3 and subtract from each of our given x's that are not x3. So we will have x3 minus x1 multiplied by x3 minus x2. So this is the general expression, and whenever we plug in our given values, we will end up with 3 multiplied by the product of x minus 0 and x minus 1 divided by negative 2 minus 0 and negative 2 minus 1. Then for our next term, we will have 1 multiplied by x plus 2. Remember that x minus negative 2 is just x plus 2, and we will have x minus 1 divided by 0 plus 2 and 0 minus 1. And for our last term, we will have negative 1 multiplied by x plus 2 and x minus 0 divided by 1 plus 2 and 1 minus 0. This, of course, can be simplified. However, it wasn't required in the course, so I was just going to stop at this answer. But it does show how we apply Lagrange interpolation and how we achieve our interpolant, which is just basically a function that agrees with the particular function at a set of known points. Next, we have a question that I had pulled from our sixth homework. This was question 2, and it asks us to find m for the integral from 0 to 1 of f of x dx equals weight 1 times f of 1 over 3 plus weight 2 times f of 2 over 3. So this question introduces another topic that was covered in the course, and it talks about finding error. So I believe I discussed in my first presentation how numerical analysis uses different techniques to make accurate approximations, and we know that approximations are not exact answers. This implies that there does exist error somewhere. So this is a basic layout of what we're going to attempt to do. We are going to set f of x equal to 1 and evaluate our first error term. And if e sub 0 equals 0, then this is an exact answer where no error exists. We then assign f of x equal to x and evaluate the second error term, which is e sub 1. We continue to do this and increase the power of x each time until we get to a point where there does exist an error. Also, I want to note, it does look a little confusing, but how I have it laid out where it says that e sub 0 equals 0, that does mean there's an exact answer. But what I'm trying to show is that it's consistent with the formula. So the actual value of the error term may not be 0, but it's showing that the equation cancels out. So if you look at the third line, f of x equals x of m. If e sub m does not equal 0, I'm not literally saying that it has to equal 0, but I'm just trying to show that it's not consistent, and therefore that's where the error lies. So in order to solve this, we'll be using the direct method, and there are multiple methods that could be used to solve this, Taylor series method being an example. However, the direct method is more direct, hence the name, and it provides a natural basis for generalization to other classes of functions. So for polynomials, it looks like the Taylor series method, but it does have a different approach to the error. And so basically what I'm saying from all of this is that we're going to try to find the first index m for which x of m fails the formula. That's what I was talking about, where e sub m, it doesn't literally have to be the value 0, but it just shows that it fails the formula, that it's inconsistent. So we will start with e sub 1 by replacing f of x with 1 and calculate the integral from 0 to 1 of 1, and this will just equal 1. We then have 1 equals weight 1 and weight 2. We then need to make this equation true, and in order to make this true, we can assign each weight as 1/2 and get 1/2 plus 1/2 equals 1. This is consistent with the formula, so we continue since we have not found any error yet. We will then set our second error term, e sub 1, and replace f of x with x, and calculate the integral from 0 to 1 of x, and this will just equal 1/2. We then set 1/2 equal to our formula, 1 over 3 times weight 1 plus 2 over 3 times weight 2. Again, we need to make this equation true, so remember in our last iteration, we assigned each weight to 1/2. We can just plug these values into our formula and see if it's true. So we have 1 over 3 times 1/2 plus 2 over 3 times 1/2 and end up with 1/2. We know 1/2 equals 1/2, so this equation is true, and this just means that we need to repeat since we're trying to find inconsistency. So we will then set our third error term, e sub 2, and replace f of x with x squared, because remember we need to increase the power of x with each iteration. We then calculate the integral from 0 to 1 of x squared, and this will just equal 1 over 3. We then set this equal to our given formula, but remember we need to square 1 over 3 and 2 over 3 in this equation. So we have 1 over 3 equals 1 over 3 squared times weight 1 plus 2 over 3 squared times weight 2. Again, we need to evaluate this to see if it's true. So we plug in our weight values and have 1 over 3 equals 1 over 3 squared times 1/2 plus 2 over 3 squared times 1/3. This gives us 5 over 18. We see that this equation is false, since 5 over 18 does not equal 1 over 3. This is the first iteration where there contains inconsistency, where there contains error. Then we see that x squared failed the formula. Then we have found our index m, where m equals 2, and we have found our answer. So I want to thank you guys for listening. Even though it was just a couple questions, these did relate to the topics that I had a lot of trouble grasping when taking the course. Hopefully this helps anyone who didn't understand these topics too well, or for anyone who hasn't taken the course. I hope this helps get a good idea for what you will be going over, but thank you so much for listening.